These are the third notes on solutions. This time we're going to discuss the concept of polarity, another phenomenon that causes things to either mix or not mix. Polarity is very closely linked to solubility, the ability to make a solution. So we are going to discuss them together. Solubility is the ability of one substance to dissolve in another at a given temperature and pressure, and we express that in terms of the amount of solute that will dissolve in a given amount of solvent to produce a saturated solution. When anything is saturated, that means it is fully loaded. It has as much as it can take, as much as it can hold at a given temperature and pressure. So for example, if your schedule is saturated, that means you've got a class every period. It would be unsaturated if you had, let's say, a free period, which maybe you'll get senior year. The rule of thumb when it comes to solubility is that polar compounds tend to dissolve in other polar compounds. In other words, your solute and your solvent would both be polar in that situation. And non-polar compounds tend to dissolve in other non-polar compounds. That means your solute and your solvent would both be non-polar chemicals. So water, which is the so-called universal solvent, which is water? Is it polar or non-polar? You should know this. Let me think. Think about the bonds and the shape. Oh yeah, water is very, very polar. So because water is a polar molecule, we'll look at the rule up above. That means that water should dissolve what? Polar compounds, because water itself is polar. So if water is your solvent, then you better have a polar solute. So then why is it called the universal solvent? Because actually there's quite a lot of chemicals that are non-polar and it can't really dissolve those. So why is it called the universal solvent? Well, in solutions chemistry, there is a weird use of the word polar. Ionic compounds like salt, like sodium chloride, are always considered polar in solutions chemistry. This is an unusual use of the word polar because actually ionic compounds aren't normally what we would call polar. Well, yes, there are positives and negatives, but they're not on opposite ends of a molecule. They are sort of separate ions that are ionically bonded together in a crystal lattice. But anyway, but in this case, that's what they do. So just realize this is an unusual use of the word polar, but because we throw ionic compounds into that category now, well, that really ups the numbers for water. So if water can dissolve polar compounds, polar molecules, and ionic compounds, which are considered polar in this situation, well, that gives you most chemicals. That is why water is considered to be the universal solvent. Better at making solutions than any other solvent. So why does this happen? When making a solution, why does that rule apply? Well, to understand this, I'll explain it first, then I'll show you a visual. When nonpolar molecules are mixed with nonpolar molecules, the intermolecular forces, that's the attraction between them, are about the same. Thus, nonpolar molecules are generally soluble with each other. In other words, most molecules will attract other molecules, even nonpolar. But the amount that nonpolar molecules attract each other is very, very minimal. It's a very small attraction. But if they're all attracting each other about the same amount, it's no big deal. There's no problem there. You'll see what I mean in a moment. Okay? And the same thing goes with polar molecules. Well, they're all attracting each other, but actually in that case, much more strongly. But as long as there's always something to grab hold of, a plus or a minus end, positive or negative end, well then that's fine. You'll see what I mean in a moment. So the rule is described as like dissolves like. It's a very short way of saying polar dissolves polar, nonpolar dissolves nonpolar. There are some chemicals that are so soluble with each other, they are completely soluble. And they are described as being miscible. If two chemicals are miscible, that means you can put them in any ratio. That means you could put in any amount of solute and any amount of solvent in any combination. You can even switch which one of them is the solvent. So there's an example with acetic acid and water. So you could make a very, very low concentration of acetic acid where it's vast majority water, let's say 99% water. You could even get them closer to the point where it's about half and half. Or you could get to the situation where it's essentially all acetic acid, what we call glacial acetic acid, with just a little tiny bit of water mixed in. So in that situation, water would not be the solvent. That would be an example of where water could be the solute if it's the lesser chemical. But that doesn't happen a lot with water. Generally, water is the solvent. So if you ever have to guess, you usually want to guess that it's the solvent. Like dissolves like. You've got to know this rule. This is the number one reason. There's a few other reasons, we won't be getting to all of them, that chemicals will mix with each other, depending on their polarity. So just remember, nonpolar dissolves nonpolar, polar dissolves polar, but if you try to cross them, nonpolar dissolving polar or polar dissolving nonpolar, it won't work, generally. So let's imagine the universal solvent if it was pure water. For simplicity's sake here, I am not showing the motion of the molecules or the more chaotic distribution of the molecules in a liquid. This looks an awful lot like frozen water, like an ice cube. But let's just imagine that this is water in liquid form, just very, very straightened out, very simplified. Well, turns out every oxygen molecule has a delta negative on the end of the molecule, on the oxygen end. I'm going to show it just on a few of these here, okay? And on the hydrogen end, there is a delta positive side on every one of the hydrogen sides, on where both of the hydrogen are located. So it turns out that's great because positives and negatives attract. So between neighboring molecules, there's an attraction, okay, that makes them drawn together. That's why water molecules like to stick together in a drop of water. That's why there's surface tension. When you slap the surface of water, when you belly flop, for example, or just slap it with your hand, you feel that strong resistance. That's because water molecules are tight with each other. They don't want to separate. They're holding on to each other as much as they can, even when they're liquid. Okay? So what would happen if I were to mix in a polar solvent? Well, if you mix in a polar solvent, notice, just like we said before, well, the oxygen has a delta negative side. We'll put it on here on a few of these, here. And the hydrogen has a positive side. I'll put it on a few of these here, I guess, right there. Okay, but guess what? These newcomers that are being mixed in, this solute that is also polar, also has a negative side on this end. Here's a negative side. I'll show it on a few of these on this one. And it also has its own positive side. So you know what? Water's fine with that because water is attracted to positives and negatives. And as long as something has a positive and negative end, well, water can deal with that. Water can stick to it. The thing water has a problem with is something with no positive or negative end. It has nothing to stick to, nothing to hold on to. So water's happy with positives and negatives and polar molecules, but what it's not happy with is when they're not polar. So now back to the universal solvent. Remember, water likes to hold closely together. It doesn't like to separate from the neighboring water molecules. So what if we tried to mix in something that was nonpolar? Well, notice these nonpolar molecules are just here minding their own business. Let's say I dump them in from above and they drop into the body of water, plunging inside. Well, now they're surrounded by water molecules. But here's the problem. The water molecules have nothing to grab onto. Those nonpolar molecules aren't repelling the water, they're just not attracting it. And water molecules do attract each other, so it's kind of like those guys are just in the way. So what water molecules actually do is they basically shove them out of the way to get to the other water molecules, like so. And then you wind up separating out the two chemicals. Well, does that look homogeneous? That is clearly heterogeneous. You get a separation of the two chemicals into layers. Those layers are often determined by the density. So whichever chemical is denser will go to the bottom, and whichever one is rarer or less dense will go to the top. So when they separate, the material doesn't always go above the water, sometimes it goes below the water. So this gives rise to that old expression, oil and water don't mix. Because oil, pretty much any oil, whether it's vegetable oil or petroleum oil, pretty much any kind of oil is non-polar. And water, of course, is very, very polar. So oil and water don't mix. That's actually an old expression that talks about polarity. A lot of people think it's due only to the density, but it is possible to get two chemicals with similar densities to mix as long as they have the same polarity. The number one reason that oil and water don't mix is their different polarities. On the other hand, if you had a non-polar solvent, let's say like oil, if oil itself was your non-polar solvent, well, remember, these molecules are barely attracting each other, just a little tiny bit, not nearly as much as the polar water molecules were. And if you insert any other nonpolar molecule as a solute, let's say like benzene, well, the attraction between the molecules is still about the same. They will attract those just as much as they will other oil molecules. So there's no big problem here. There's no need to force them out of the situation, to force them into a separate layer. So nonpolar molecules will mix with each other because the attraction between them is very similar. It's on the same scale, at least. So that's a simple explanation for why nonpolar mixes with nonpolar. Here is a diagram of where the solute is actually polar, but the surrounding solvent is nonpolar. So the solvent doesn't have much of a problem with this. It's just mildly attracting neighboring solvent particles. However, all of these little solute polar molecules have a strong attraction to each other, and so they begin to pull each other together. And depending on their density, that will determine whether this pulls them in an upward or downward direction. And what you wind up with is separated heterogeneous layers, not a solution. So notice that this was driven by the polar molecules' attraction to one another, not so much by the nonpolar solvent, okay, but by the polar solute in this case. So it's really the polar molecules that drive the separation of the two whenever they get mixed. You know, like we said before, oil and water don't mix, okay, and polar and nonpolar don't mix, with very few exceptions. Ionic compounds are considered polar in solutions chemistry because they do have positives and negatives. It's just that those can be easily separated by a strong enough polar molecule, and that's exactly what happens when salt dissolves in water. Water comes along on the surface of the salt crystal, on the corners and the surfaces, starts shredding them apart, and so what you wind up with is, after the ions are pulled out of the crystal lattice by the surrounding water molecules, you wind up with separated ions floating around in solution with water. Water loves cations because water has a delta negative side. Notice that sodium ion is surrounded by the oxygen end of the water molecule that like to stick to it. It loves anions because they have a negative charge, and water has a delta positive side that can stick to that. Notice the chloride ions are surrounded by the hydrogen ends of the water molecules. So water loves ionic compounds for the most part. They are mostly soluble in water, and it will shred them apart and make a solution. So in solutions chemistry, again, ionic compounds are considered to be polar. And it doesn't have to specifically be sodium chloride. It could be any ionic compound that, of course, can be split apart into its cation and its anion. And that's what water usually does. Even if that cation or anion is a polyatomic ion, or if they're both polyatomic ions, it might look a little more complicated when you see it, but it's the same basic idea. It's still a big particle with a positive charge and a big particle with a negative charge. So water likes to dissolve those as well. The next phenomenon we are going to look at is conductivity. Some solutions will conduct an electrical current, and you can tell that using a conductivity indicator as shown in that picture if it lights up. And those solutions are described as containing electrolytes. So this is something that we will be observing in some of our labs. Electrolytes are chemicals that form ions when they're put in solution. And those ions are capable of conducting electricity. The reason they are is because they're positive and negative particles that can freely move around. If they can freely move around, they can transmit an electrical current. So they're called electrolytes. Ionic compounds like sodium chloride are dissolved into electrolytes in solution. So wait a second, that's one chemical, NaCl, producing two particles, the sodium ion and the chloride ion. So they actually produce more particles per mole than what we call non-electrolytes. That's another one of those great names where something is defined by what it is not. A non-electrolyte is a molecule that remains intact when you put it in solution, something that doesn't break into ions. So it turns out that electrolytes have a greater colligative effect than non-electrolytes. An example of a non-electrolyte would be ethylene glycol, like we used in the antifreeze lab. They remain intact, so there's just one particle when it's in solution. An ionic compound will split into two or more particles, making twice as many per solution. That has a bigger effect on lowering the freezing point. If you got more particles, that's going to have a bigger effect. It's also going to have a bigger effect on elevating the boiling point. Those are the colligative properties. Water containing electrolytes conducts electricity. So I like to think of the word electrolyte. It sounds like electric light. And if you have electrolytes, well, then it will light up the electric light. Think of it that way. By the way, I'll just mention briefly that there are some molecules that are electrolytes that can actually be ripped apart when put into solution. And some of those are acids. Many acids are molecules that can be ripped apart when put into water, and we'll talk about that in our next unit. So why does this happen? Because non-electrolytes, even though they may have polar ends, those two polar ends are connected to one molecule. They can't move around separately. But that's not the case if you have ions. Ions can move freely. So if there's an electrical current, they can flow in one direction or the other, either way conducting electricity. And so if you put a separated circuit into your solution, and if there are electrolytes inside the solution, they will complete the circuit, allowing the light to be turned on. The more of them you have, the brighter the light will be. And if you just have a few, the light will be very dim. Honestly, it's very hard to get away from ions unless you have a super clean beaker that's got nothing in it whatsoever. If you have really, really good distilled water that hasn't been contaminated, it's very hard to get away from ions. They're just going to be around, at least in small quantities. So remember, an electrolyte is when the electric light lights up in solution. Once you have a mixture, well, sometimes you might want to separate it again back into the two or more chemicals that make it up. And sometimes that's easy, and sometimes that can be challenging. If it's a heterogeneous mixture, well, there's a few easy ways to do it then. You could do what is called decanting. Decanting is just pouring off the layer on top. If you pour off one layer, well, you're left with the layer below it, and now you've separated the mixtures. That only works if it's a heterogeneous mixture, one of those bad mixtures. Okay. You could also separate them using a centrifuge, separating them by density. You could use filtration to separate them if they're different sized particles, or you could just wait for one of the materials to evaporate over time. Another way to separate mixtures is chromatography. The advantage to chromatography is it will actually work on homogeneous mixtures as well. It'll pull different chemicals out of solution based on the attraction to paper, but chromatography has its limitations, and it's not my favorite way of separating solutions. The best way to separate a solution is definitely distillation. As long as they have two different boiling points, well, you can boil off one of the chemicals and leave the other one behind. If you boil off one chemical and capture that and condense it somewhere else, that is what is called a distillate. A distillate is something like distilled water or distilled vinegar, something that has been concentrated by distillation. So generally the way we do it is we boil one off and collect that one, and that is the distillate. But then the one that is left behind can also be relatively pure, and you've pretty much separated your solution. It gets a little trickier when it's a mixture of more than two chemicals, which we usually have in the world. So you have to do it's a longer process. But basically, think of distillation is boiling off one of the chemicals, like let's say the water, and leaving the other one behind. If you want to know if a chemical is soluble with water, then you really want to know your solubility table. On page 473, there is a solubility table. And make sure that you're reading this correctly. The chemicals on the top, the chemicals shown on the top are actually soluble in water. So pretty much anything that has an acetate or an alkali metal, that's an important group. Ammonium, bromides, if it has those in it, it's pretty much going to be soluble in water. Okay? Unless it's one of the exceptions. Notice that there are some exceptions, like acetates containing iron, for example. Okay? Alkali metals only have one exception, lithium fluoride. Okay? So as long as it's not one of those exceptions, then the groups of chemicals on the left will be soluble. And there's a lot of acetates. There's a lot of compounds with alkali metals. That's an understatement. In fact, you could say that's one of the reasons that water is the universal solvent, because of those alkali metals making everything soluble in water except for lithium fluoride. Lower down on the table, we see the opposite. We see chemicals that are insoluble in water. That means carbonates are not soluble. Chromates are not soluble. Hydroxides are not soluble. Unless it's one of the exceptions. Oh, look, group 1. Group 1. Those are the alkali metals. So why is group 1 in every one of these exception categories? Oh yeah, because look above, alkali metals are soluble in water. So if you mix them with pretty much anything, with that one exception, it will make something soluble in water, which again is one of the reasons that water is the universal solvent. Why does it say group 1 instead of just alkali metals? Well, there's another important element in group 1 that is definitely not an alkali metal because it's not a metal. Hydrogen. Hydrogen is in group 1, the most abundant element in the universe. So you can't just ignore that. So when they say group 1 instead of just alkali metals, that's because they want to include hydrogen as well. So make sure that you're familiar with how to read this solubility table, and we'll be using it later on. So now you should understand a little bit more about why some chemicals will make a solution and others will not, and also why some chemicals are electrolytes and others are not. And that is the end of the Notes on Solutions, Part 3. Thank you very much.